Today's lesson is going to be on ensemble methods for machine learning, which operate under the principle that the whole is greater than the sum of its parts. So here's today's lesson. I'm going to give an ensemble learning overview. I'm going to talk about weak versus strong learners, as well as bias versus variance. Then I'm going to talk about the three main ensemble methods: bagging, boosting, and stacking. And finally, we're going to work through a practical Jupyter Notebook example using a random forest model, which is an example of a bagging ensemble method. And we're going to look at the Titanic dataset, which is hosted on Kaggle, and try to answer the question, what characteristics make a passenger most likely to survive? So what exactly are ensemble learning methods? So these are methods that take multiple models, which are known as weak learners, and trains and combines them to create a strong learner or ensemble model. So this is an example of a random forest classifier, which, as I mentioned in the intro, is a type of bagging classifier. So in this image, the top line labeled all data is the initial data set. This data set is broken up into smaller subsets of data. And a decision tree is fit to each of these subsets of data. So these decision trees are the weak learners, which when combined, make up the random forest. The hypothesis here is that by correctly combining weak learners, you can produce more accurate and powerful results. So what is a weak learner? A weak learner is a model that performs only slightly better than random guessing. In addition to having these poor predictive capacities, remember they're only slightly better than random guessing, they usually have either extremely high bias or variance. So in the kind of lighthearted example here, we have the blind data scientist attempting to correctly classify this animal that they only have access to a portion of it. So the scientist in the front is feeling the tusks and says, I think it's a spear. And the scientist feeling the trunk says, no, it's a snake. And the scientist on top, he's waving the ear back and forth, and he's saying, I think it's a fan. So you can see that each of these data scientists only has access to a small portion of the data. The idea here is that by combining these models through ensemble learning, you can help overcome these problems of poor predictive capacity and high bias or variance. So if you imagine this, that these scientists are your weak learners, if you've got 100 of them, and they're all feeling this elephant, all different parts of this elephant, and they're able to combine their predictions, you could probably have something very close to an elephant as your output. Now you might get a rhinoceros, but you're unlikely to get a dog or a fish back. So as mentioned, there are three main ensemble methods. We've got bagging, boosting, and stacking. So bagging and boosting use homogeneous weak learners. So what that means is that each of the learners which make up the ensemble method are going to be of the same type. So for example, random forest uses decision trees. Other methods might use linear regression or logistic regression. But whatever you're using, you're going to use the same type throughout the method. In contrast, stacking uses heterogeneous weak learners. So you might use a decision tree on a single portion of the data. You might use a linear regression on another part of the data, etc., etc. Bagging and stacking are able to learn independently and in parallel. So that means each of the models are running. They're not talking to each other. They're not influencing each other. And they're all running at the same time. Boosting learns sequentially, which is to say learner A influences learner B, who influences learner C, etc., etc. Finally, bagging and boosting combine their models deterministically. So what that means is that all of these weak learners, they perform the statistical analysis, and then their outputs are all combined in some kind of purely non-statistical fashion, either by averaging or some other method. In contrast, stacking combines its outputs probabilistically. Now that's because in stacking, all of the weak learners' outputs are taken as inputs for a meta model or second level model. So let's dive a little bit deeper into each of these methods, starting with bagging, which is short for bootstrap aggregating. So bootstrapping is the process of drawing L samples of size B with replacement from a data set of size M where B is less than M. So that's a lot of variables I just threw at you. So let me direct your attention to this example where we have an initial data set of size 12. So M equals 12. It's the 12 numbers in blue here. And from that data set of size 12, you're taking bootstrap samples of size 5. So B equals 5 in this case. So the first sample you have 1, 10, 3, 8, and 3. So you have 3 in there twice. That's because you're drawing these samples with replacement. The second sample you have 4, 2, 11, 9, and 3, and so forth to the elf sample, the final sample, which has 5, 12, 1, 5, and 6. So that's also a sample that has observations drawn with replacement. So the reason you want to do that has to do with the statistical properties of these bootstrap samples. And they're considered to have good statistical properties if the following conditions are met. So first up is representativity. Now you want M to be large enough to capture the complexity of the underlying data set. So let's remember that unless you're conducting a controlled laboratory experiment, you rarely have access to the true underlying data set. So imagine that you're trying to build a model for spam detection in an email security system. You don't have access to all of the emails in the world, and usually not even all the emails in the system. You have access to a subset of that data. So it's important that M is large enough to capture the complexity of that underlying data set. The second condition is independence. So these L samples are not correlated. That's determined by two conditions. First is that M is much larger than B, so you don't want your samples to be approaching the size of the initial data set. And the second condition is this sampling with replacement. So that helps to ensure that there are fewer duplicate bootstrap samples. Can you imagine if you have 5 identical bootstrap samples, you're starting to throw artificial weight toward that observation. So you want to have as many unique samples of the data as you can, and sampling with replacement helps you control for that. So let's talk about how to represent this process mathematically. So remember, you have L samples of size B, and those can be represented mathematically as follows. So each sample is contained within a curly bracket. So you have Z1 sub 1, Z1 sub 2, through Z1 sub B. That's your first sample, and it's of size B. Your next bootstrap sample, Z2 sub 1, Z2 sub 2, etc., all the way through your final or last bootstrap sample, ZL sub 1, ZL sub 2, through ZL sub B. So in this representation, z lowercase b superscript lowercase l is equivalent to the bth observation of the elf bootstrap sample. So now we've represented our samples. Let's fit L weak learners to these samples. It's a little bit more of a simple representation. You have W sub 1 through W sub L. So you're having L weak learners because you have L samples. And then you're simply aggregating them through averaging. So the idea here is that if you're able to average these independent learners, it's going to reduce variance or overfitting. Now, if you remember, variance is a measure of the data dispersion of a data set. So statistically, it can be represented as the difference between the observed value and the average value. So you can think if the data is highly dispersed, it's going to have a high variance from the average. Now, in terms of machine learning, you can think of variance as being a difference between the particular model you're looking at and the average model. So what's going on here is that you're taking the average of all these models. So if you're averaging all these models, intuitively, it gets closer to the average. You're reducing the variance or distance from the mean. So I'll let you think about that for just a moment and write that down. So averaging occurs fairly simply here. If it's a regression problem, it's just a simple average. So the strong learner equals the sum as lowercase l goes from 1 to uppercase L of all of the weak learners. So every weak learner has an output. You just sum them up and divide by the number of weak learners. In other words, a simple average. If it's a classification problem, you need to use a majority vote. So it's a little bit more complex of a mathematical representation, but it's really no more difficult to understand here. You have something called the max cardinality. So all you're doing is counting the number of times each observation occurs, each classification occurs, and then whichever classification occurs the most, that's the strong learner. So let's say your model has 5 outputs that say it's a pear and 2 outputs that say it's an apple. The classification is then going to be pear because it's 5 to 2. So the next model we're going to discuss is boosting. So boosting is a sequential model where the learners are fit iteratively. So this is unlike bagging, where the learners operate independently and in parallel. So by operating in parallel, that just means they're all running at the same time. This is not true with boosting. In boosting, each learner feeds into the next, and subsequent learners take the worst predictions and focus on improving. So we're going to talk about this a little bit more in the next slide, but I'm going to provide a kind of sort of a lighthearted example that can help you illustrate the process of boosting and how it might work. So in this example, you have 5 people, and they're all trying to guess a number between 1 and 100. The actual value that you're thinking of is 47. So like a good data scientist, you're going to make a table and write down all these observations. So the first person, they have no idea what the actual value is, so they guess 20. You tell this person, oh, I'm sorry, 20 is very low. Okay, so person 2 then knows something. Person 2 knows that 20 is very low, so they guess 80. You say, oh, I'm sorry, 80 is very high. So person 3 now knows that the number is between 20 and 80, and that both are not very close to it. So they just split the difference and they guess 50. All right, now we're getting somewhere. You tell them, I'm sorry, 50 is too high. So person 4 now knows that it's between 20 and 50, but probably closer to 50 because 20 was too low, was very low, and 50 is just too high. So they guess 40. So you say, I'm sorry, 40 is too low. But person 5, now they know quite a bit at this point. They know that it's somewhere between 40 and 50. So they're very, very close. So they say, just split it, and they say, I'm going to guess 45. So you can see how in just 5 iterations, you can get very, very close to the actual value. Now, of course, in real life, data is rarely going to be this clean and this simple, but this is just to conceptually illustrate how boosting might work, how subsequent learning might work. Boosting is also very effective at reducing bias. So if you remember, bagging was really good at reducing variance. Well, boosting is really good at reducing bias. And we'll talk about a little bit about why that might be in a subsequent slide. But for now, it's good at reducing bias, and it's also been proven very powerful at improving accuracy. So as a little refresher, accuracy is a ratio of the correctly identified observations to the total observations. So here we have the numerator. You have true positives plus true negatives divided by true positives plus false positives plus true negatives plus false negatives. So boosting works by identifying the weakness of the predictor. So there's 2 major boosting algorithms. You have AdaBoost, which is short for adaptive boosting, and gradient boosting, which doesn't really have a cool way to shorten that name. AdaBoost is used for classification problems, whereas gradient boosting is used for classification and regression problems. AdaBoost focuses on the weakness of the previous estimator's fitting error. So how far off was that error? Gradient boosting focuses on the weakness between the predicted value and the actual value. So here we have an example of AdaBoost. So AdaBoost is, in this example, is using decision trees as your weak learners, and it's assigning weights to the incorrect values. And then sequential trees are grown considering past mistakes. So let's go ahead and walk through this. We see the results of tree 1 over on the left in this image. It has drawn the decision boundary as a vertical line on the left side. It's correctly classified those 2 blue dots and incorrectly classified the 2 blue dots at the top. Now remember, it's trying to draw a decision boundary between the blue dots and the red dots. So it tells tree 2, I've incorrectly classified these 2 blue dots. So it assigns weight to those 2 blue dots. So decision tree 2 draws a boundary as a horizontal line near the top, and it correctly classifies those 2 blue dots. However, it incorrectly classifies the red dot. So decision tree 3 draws a vertical line on the red side, and it has now correctly classified those red dots. So it combines all 3 of these outputs and comes up with the combined results, the final one on the right, which draws the correct decision boundary between the blue dots and the red dots. So this is kind of a clue as to why boosting reduces bias. So it's really right there in the definition of gradient boosting. It says it focuses on the difference between the prediction and the actual value. That's literally the definition of bias, the difference between the predicted value and the actual value. So you want to minimize that distance to have a low bias. So intuitively, boosting works by reducing bias. So unlike with bagging, which reduces variance, boosting reduces bias. So the final model I want to talk about is stacking. So stacking combines heterogeneous models to train a meta model or second level algorithm. So consider the example here on the left. We have 3 weak learners represented at the top. Y hat 1 is a decision tree. Y hat 2 is a spline regression or a multivariate regression. And Y hat 3 is a neural network. These 3 weak learners have outputs which then act as inputs for that second level algorithm, which then performs its own calculations and comes up with a new prediction. So stacking works by splitting the training data set into 2 folds, and a fold is just a data set. So it splits the data set into 2. In stacking, both the weak learners and the meta model or second level algorithm must be chosen. So you'd want to carefully consider which section of the data you'd want to use which weak learner on. And the same with the second level algorithm. And finally, learners are fit to the data in the first fold, which generates predictions. And then you fit the meta model on the second fold using those predictions, which are made by the weak learners. So there is something called multi-level stacking. You can use third level algorithms, fourth level algorithms. You can keep going as long as you need to. And really a lot of the very powerful ensemble methods use that multi-level stacking. So it's very interesting, very powerful, but it's also, you really need to know what you're doing. It's highly customizable. So in review, ensemble learning combines weak learners into strong learners to get better results. There are 3 main ensemble methods. You've got bagging, boosting, and stacking. These methods can help deal with high bias and or high variance, and many of the most powerful algorithms used today are based on ensemble learning methods. So that concludes this portion of the lesson. This is just a reminder that all students are going to be required to post to the discussion board. I want you all to post at least 1 discussion post and respond to at least 2 posts. And the instructions are here on this slide deck, which again, I will make available to all of you after this lesson. If you have any questions, please feel free to come to me. You can either email me or come to my office hours. And the next section of the lesson, we're going to work through a Jupyter Notebook example. So for this portion of the lesson, we're going to take you through a Jupyter Notebook example of a random forest classifier, which, as I mentioned, is an example of a bagging ensemble model. And we're going to look at the Titanic dataset. So the Titanic dataset contains a list of passengers on board the Titanic, whether or not they survived, as well as some personal information about them that's going to help us generate our random forest. So let's go ahead and load in our libraries, as well as read in our data sets, which can be found at this site. So you can see we've got our variables here. We've got whether or not they survived. We've got the passenger class. Hopefully most of these are self-explanatory, but we get to SIB, SP, and PARCH. SIB, SP is the number of siblings or spouses they have with them. PARCH is the number of parents and children that they have with them. So when I post this online, I'm going to post a data dictionary for you to look at. So it'll go into a little bit more detail about what each of these variables means. So let's go ahead and jump into data pre-processing. So whenever you come across a new data set, you really need to look at this data set and see some things you need to check for are there any missing values? Are there any duplicated values? So let's go ahead and check for that here. We see that there are 177 values missing in age, and then 687 missing in cabin, 2 missing in embarked. That's in the training data set. In the testing data set, we've got 86 missing in age, 327 in cabin, and 1 missing in fare. So in the training data set, there's 891 total observations. So to be missing 687 is about 3/4 of the data values. So that's something we need to think about how we want to deal with that. So in fact, we need to address each of these null values because machine learning algorithms don't really understand what to do with nulls. Most machine learning algorithms, unless you specify otherwise, will either completely ignore a row. Any row that has missing data, it'll just ignore that row, or it will throw an error, which in fact, this classifier will throw an error if you attempt to run it on a null data set. So let's go ahead and so we need to deal with each of these variables. So I'm going to go ahead and delete the cabin feature because, again, 3/4 of the total values are missing. So let's think about what we want to do with the other data sets. Each one we need to sort of carefully consider. So let's first look at the embarkation ports. So we've got 644 from port S. So it's by far has the greatest number of people embarking from that port. So I'm going to fill in that data with the median. So there's 2 missing values in the embarked field. I'm going to fill it in with the median, with the most common value. And if you remember, we had 1 value missing from fare. I'm just going to fill that in with the mean. That's a very legitimate and well accepted data imputation method in situations such as this, where there's very few data values that are missing relative to the size of the entire data set. So we can see now those 2 values have been assigned to the S embarkation port, and we've also filled in the value for the fare with the mean value. So we have one more field that we need to deal with, and that's age. That's going to require a little more subtlety than just filling in with the mean. So something that becomes apparent when you look at this, the data set, is that the name field has something else in it, and that's the title. So I'm going to take the average age by title for each person. So we have titles Miss, Mrs., Miss, Mr., Master, and Doctor. And here, Master is just kind of an old-timey way of denoting, it's like a young boy. So I have an idea that Mr. will be older than Master and Mrs. will be older than Miss. So I'm going to take the mean of those and fill it in. And our intuition was correct here. We can see that the average age of Mr. was 33, whereas the average age of Master was not even 5. So there's quite a difference. So it makes a lot more sense to use the average by title than to use it by just the average, the global average. So now let's check to make sure we got all the nulls. Great, no nulls, perfect. So we can go on. So now let's do some feature engineering. So if you remember, there's these fields called sib, sp, and parch. So that's siblings and spouses, and then parents and children. So let's kind of visualize that data. So most people are not traveling. They do not have a sibling or a spouse, and they do not have parents or children. So let's create a field called new field called alone and one called family member. So if family members plus spouses is 0, you get coded as alone, and then you also get a count of your family members in the family member field. And I generated these nice visualizations, survivors by sex, survivors by class. You can kind of look through these if you would like. I'm going to leave them up here. Again, this notebook will be posted for public review, but just in the nature of for time, I'm going to avoid discussing them here. So we're almost done. Finally, we need to create some dummy variables. We need to deal with the data that is coded as a categorical. So, just as I said, machine learning algorithms can't handle nulls. They also can't handle human speech. They don't know what female means. They don't know what that means. So, unless you're dealing with like an NLP, like a specifically designed algorithm to deal with language, they will throw an error. So, I am coding sex from female to male to 1 and 0. So female is 1, male is 0. And I'm breaking up the ports so that each one gets its own category. Port S, port C, and port Q. And then I'm dropping the features which I don't think are going to be relevant to determining whether or not somebody survived. So I went ahead and did that. And then let's go ahead and look at the data. So again, head. We've got the P class here. We've got the correctly identified sex. We've got our ports. And then we have these new features, alone and family members. So let's go ahead and look at something called a correlation matrix. So correlation matrix shows how each variable is correlated to each other variable. So it's kind of this impressive looking graph, but let's walk through it real quick. You might see that there's a 1 all the way in a diagonal line. So that's because each variable is correlated 100% to itself. So survived is correlated 100% with survived. That makes sense. So I'm going to direct your attention to this top row of survived. That's the variable we're trying to predict. So you can see that P class is the first one. It's a negative correlation, which makes sense. Third class were least likely to survive. So the higher your class, less likely you were to survive. Sex is positively correlated. 1 was female, they're more likely to survive. This all makes sense to us. Now I'm going to generate the random forest classifier. You can kind of look at this. I put some comments in here which can kind of help you understand it. And again, feel free to ask me any questions which you like. But for now, I'm just going to go ahead and run it. I've run the classifier. Most of these, or I guess all of these, are pulled in from sklearn or scikit-learn, a very powerful and important library for data science. And I'm going to go ahead and generate the feature importance graph, which really can kind of pull it all together and give you a view of exactly what's going on. So here we have the features which are the most important to determining whether someone survived or not. So we have age and sex as the most important, tied. Then we have fair, P class, and then family member. So if age is the most important, and if you look back up at that correlation matrix, it was negatively correlated. So the younger people were more likely to survive. So we have age is the most important, sex is the second most. So sex was a positive correlation. So that's female was more likely to survive than male. And then fair was next. So that's a positive correlation again. If you paid a lot of money, you're more likely to survive. So let's put that in another term. If you are a relatively young woman who paid a lot of money for her ticket and is sitting in first class, and you're traveling with a spouse or a child, you're the most likely to survive on board this ship. On the other chance, if you're a relatively older man who didn't pay very much for his ticket at all, and you traveled in third class or steerage and you're traveling alone, you have the worst chance of surviving. So that's the basic way that you can analyze that you can run a random forest classifier in Jupyter Notebook. And again, this concludes our lesson. Feel free to ask me any questions either through email or during office hours. Thank you very much. And don't forget to complete your discussion posts.